Okay, so let's look at another one that's kind of tricky here. Okay, let's look at one with absolute values. Okay, so that's how we have this, and that's not a directional limit for ourselves, but man, I think I need to make it a directional limit here because it's dealing with absolute values. So when you have an absolute value, the best thing to do here is to make it into make this into a piecewise function, because that's all absolute values are. They're fancy piecewise functions. So the easiest way to do that is to do the two different directions. So if I'm going to go from the left of it, right? If I do the left, then this is going to be negative, so the absolute value is going to make it positive. So I could rewrite it like that. Okay, because this would have spit out a negative number, and the absolute value would have changed the sign to a positive. All right, I'm going to multiply it by negative, so it changes it to a positive. Okay. Similarly, the limit, or if limit as x approaches 1 from the right, if I look at the top there, right, this is going to be a positive number. Absolute value is going to do nothing, so I'll just write it like that. Okay. So if you have an absolute value, write it as a directional limit. So it's kind of like a piecewise function. Or I could break it up and show the two pieces, but the limits allow me, instead of writing it as a piecewise function where I have domain restrictions, this just kind of puts it into the right context for me. Okay. So if I reduce this, that's going to be the same as x minus 1, x plus 1. So if I reduce that function and find the limit of the reduced form, I'll have x plus 1 on top and negative 1 on the bottom. So my limit here is going to be negative 2. So my left-hand limit is going to be negative 2. Okay. Let's see, I do it from the right. I say this is going to reduce the same way. The numerator, x minus 1, x plus 1. So it reduces down to x plus 1. And I get 2 there. So I see the left-hand limit's negative 2 and the right-hand limit's 2. Right? So I can see that this whole limit does not exist. And that was because my directional limits did not agree. Okay. By the way, if I ask you for justification on does not exist for these, right, just showing the directional limits not being equal, that's great. That's enough justification right there. All right, you've already got it. Okay. So absolute values involve you doing two directions. What about a piecewise function? Okay, so let's look at the piecewise function. Let's say we had, let's see, yeah, I'll do this. What about the step function? Sorry, I don't know if I said piecewise. Okay, so let's say we have this. Okay, the limit as x approaches 1 of the step function, right, the greatest integer function here. Right, remember that sometimes in textbooks this is written as, right, this right here is the same as int of x. I mentioned that in a previous video, and then I got questions from people. I didn't know what int meant on the homework. Right, so make sure that you pay attention to that. Use your notes to do these in case it says that. Anyway, so coming back here, so I'm going to do the same thing because the piecewise, this again is a piecewise function here, right? A step function, because that's what gives it all. The steps are actually the pieces going from one to the next to the next. Okay, so let me do the two directional limits. Okay. So the top, if I'm from the left, right, if I plug in a number to the step function, and it's a little bit less than 1, like 0.9, 0.99, 0.999, the step function rounds it down to 0. So the top is negative 1. It's not even approaching negative 1, it is negative 1. And that's what's kind of weird about the step function here. Okay, since the actual value and it's not approaching that value, right? That kind of supersedes things. Like, so if you're at 0.9, 0.99, 0.999, the value is negative 1 no matter what. So you are at negative 1, not approaching negative 1 for the numerator value. Okay, for the denominator, if I'm a little bit less, 0.9, 0.99, 0.999, I am approaching 0, but it's a negative number and it's negative small. The negatives cancel, and I'm left with infinity there. So the left-hand limit is approaching infinity. Let's think about the right-hand limit. This one is even trickier to conceptualize, so bear with me on this. You may have to watch this part of the video a couple times. Okay? So if I plug in 1.1, 1.01, 1.0001, and I subtract 1, right? Actually, I'm sorry, don't subtract 1. First, you round down. Okay, so 1.1, 1.101, 1.001. The value of this is going to spit out 1 every single time. It's not approaching 1, it is 1. Right? So therefore, the top is 0 no matter what. Because you're taking this value that's always 1 and subtracting 1, the top is 0. Not even approaching 0. That's an actual value. Okay? The denominator is approaching is a positive small. It's approaching 0, but it's not actually 0, but it's approaching it, so it's positive small. Okay? So 0 divided by anything is 0. Okay? Now, if the top was approaching 0 and the bottom was approaching 0, we'd have to do this totally different. But because the top is an actual value of 0 no matter what, that's why this answer is 0 there. Okay? So that's a tricky one for yourself. Okay? Okay. So in my opinion, that's the hardest one there, right, to do. Well, good luck with those examples, right? Do your very best, and let me know if you have questions.